Hello students, welcome to EPG Pathshala. I am Dr. Aranya Bhattacharjee from the School of Physical Sciences, Jawaharlal Nehru University, New Delhi. Today we are going to discuss about the module Excitations, that is spin waves, from the paper Solid State Physics. So students, let us see what we are going to learn in this module. First thing, understand the concept of spin waves, which are also known as magnons. Learn about Holstein-Primakoff transformation to solve the spin Hamiltonian. So, this is a special technique, very special transformation that you have to learn to solve spin Hamiltonians. Learn how to calculate the ground state of the spin Hamiltonian using semi-classical approach. So, the first thing that one should learn when you are given a Hamiltonian is to calculate the ground state. Then how the spin Hamiltonian is solved in the large spin limit to generate the spin wave dispersion. This is also one of the very prime results of solving spin Hamiltonian, that is to generate the spin wave dispersion. And then finally, from the spin wave dispersion you will learn about what are the famous Goldstone modes. The ferromagnetic ground state of the Heisenberg Hamiltonian is maximally polarized, that is L into S, where L is the number of lattice sites. But what does it mean? That it is maximally polarized because why? All the spins are pointing in the same direction. That is why it is maximally polarized. Low-lying excitations can be created by turning the jth spin from Sjz to S to Sjz to S minus 1, and then allowing this deformation to propagate through the crystal like a plane wave. So, try to understand this. So, these excitations are spin wave. So, you are basically disturbing one site and that is propagated. A quasi particle that is created when a spin wave is excited is called a magnon. So, magnons are quantized magnetization density waves. So, this figure actually beautifully illustrates the spin waves in one direction. So, if you look at this figure carefully, you will see that what we had just said, that you sort of create a disturbance in one lattice and you allow that to propagate. So, you see that if you look at the left side and then you can imagine that the spin, so assume that like all the spins are pointing up, let us say in a one direction, they are all pointing up. No, there is no spin wave excitation. Then you slightly tilt one of the spins, let us say in the extreme left, and then what you do is that you allow that tilt, but the angle by which it has been tilted, to travel. So, it will travel throughout the lattice. So, this is basically a one dimensional representation, and you can see beautifully a sinusoidal kind of a curve is produced, which is basically representing the spin wave. So, what exactly is the Holstein-Primakoff transformation? This can be done using now a Schrödinger representation. That is basically Schrödinger representation means that in this specific case where you are replacing the spins by bosonic operators. So, we will now wish to express the magnon creation and destruction operators in terms of the spin operators. In this new representation, the spins are represented by Bose operators. So, okay students, so now we will try to understand what exactly is Holstein-Primakoff transformation. See, we now wish to express the magnon creation and destruction operators in terms of the spin operators. So, in the Heisenberg Hamiltonian, we had used product of fermion creation and annihilation operators, but now in this new representation, the spins are represented by Bose operators. Now, adopting the Schrödinger representation, so let A1 dagger and A2 dagger be two boson creation operators. Okay. For each site, then we have three spin operators, Sjx, Sjy and Sjz. So Sj basically represents the spin at the jth side, and the components are included in the superscript x, y and z, and they are coupled to the identity. This identity is very important. Sjx square plus Sjy square plus Sz square is equal to S into S plus 1, where S is the total spin. Okay, so this last identity which I have just said is very important, and it will be used throughout this module. Now we can write these spin operators or the spin components which we have described in terms of the bosonic operators A1 dagger, A1, A2 dagger and A2. Okay, so this is basically the aim. That's what I had already said, that I want to write, rewrite these spins in terms of these bosonic operators. So this is basically one of the essence of the Holstein-Primakoff transformation. So this is very important. So the x component of the spin is written like this: Sx is equal to half A1 dagger A2 plus A2 dagger A1. Also, it's very note also this thing very important, that you see in Sx the second part A2 dagger A1 is basically the Hermitian conjugate of this A1 dagger A2. Okay, so as you can see that when we take this Hermitian conjugate, the A2 operator, which is appearing as a destruction on the first term, now appears as a creation, but it moves to the left of A1. Okay, so you have to take that into consideration. This is very important from the quantum mechanics point of view. And Sy is half of A2 dagger A1 minus A1 dagger A2, and also Sz is half of A1 dagger A1 plus A2 dagger A2. So this is like a very important three relations that we have just studied. Now the spin operators obey the commutation relation for angular momentum operators. Okay, so what is basically the commutation relation for the angular momentum operators is applicable here. So I write here one example, that is the commutation of the spin component Sx and Sy is equal to iota by 4 A1 dagger A2 plus A2 dagger A1 comma A2 dagger A1 minus A1 dagger A2. The commutation of these two gives me iota Sz. Okay, so actually you can verify this also. This is very important, and at the same time we also have the relations, that is S plus, which is basically an operator, is equal to A1 dagger A2, and S minus operator is equal to A2 dagger A1. So they are basically conjugate of each other. Notice that. Now stepping the spin down by one step is like creating a boson. However, we cannot equate Aj dagger with Sj minus. Okay, don't confuse with this. So if one wants to describe particles of spin, then the following relation should be satisfied. So total spin S is equal to half A1 dagger A1 plus A2 dagger A2. Now this equation will be satisfied only if A2 is equal to under root of 2s minus A1 dagger A1. Okay, and also S plus can be written as A1 dagger into under root of 2s minus A1 dagger A1. S minus is equal to under root of 2s minus A1 dagger A1 into A1. So you see that why I am saying S plus and S minus are conjugate of each other, Hermitian conjugate. So if you take the conjugate of S plus, you will immediately see that the term in under root does not change, but what changes is that A1 dagger becomes A1, but it goes to the right hand side of the under root when it was existing in the case of S plus on the left hand side. Okay, you have to be very careful. These are small things, but they matter a lot. And at the same time, you have Sz is equal to A1 dagger A1 minus S, and the standard spin commutation relation, commutation between S plus and S negative, is equal to twice of Sz, is always satisfied. Now in order to express the Z component of the spin, that is Sz, as A1 dagger and A1, we can write Sz square is equal to S into S plus 1 minus half of S plus into S minus plus S minus into S plus. Now we already have these relations for S plus and S minus, which we have already defined. So you can substitute them here, and by substituting this we get this expression, that is Sz square is equal to S into S plus 1 minus S, a whole bracket. You have this quantity, that A1 dagger into 1 minus A1 dagger A1 divided by 2S multiplied by A1 plus under root of brackets 1 minus A1 dagger A1 divided by 2S multiplied by A1 into A1 dagger again multiplied by in brackets 1 minus A1 dagger A1 divided by 2S. So you can sort of have a look at this expression, and then immediately you get to see that how you can sort of simplify this, and after simplification you can see that this reduces to Sz whole square is equal to S minus A1 dagger A1 whole square, and then taking the under root of both sides you will see that Sz finally is equal to S minus A1 dagger A1. So with this equation for Sz, we can conclude that the number of bosons is equal to the number of times the spin has been stepped down. So each time you step down the spin, you create a boson. Okay, see, you see the connection between the two. Now let us talk about the ground state energy and what we mean by Goldstone modes. So we already are familiar from our previous 3-4 slides about the Holstein-Primakoff transformation. And then we have already said that we want to write these spins in terms of the bosonic modes. So now let us now go back to the Heisenberg-Hamiltonian. We now proceed to solve the Heisenberg-Hamiltonian by assuming that this S, total S, the spin, to be very large. We are assuming a very large spin and expanding in 1 by S. Okay. So I say that S is large but expanding in 1 by S. So S large means 1 by S is small. Okay. So try to note this important point. So the dot product of two different spins at two different sides, let's say ith side and jth side, Si dot Sj is equal to half of Si plus into Sj negative plus Sj plus into Si negative plus Siz into Sjz. Okay, so this is standard quantum mechanics from textbook. You can see this, but this is a standard result. And then putting in the values expressions for S plus and S minus from our previous slides, you get to see this is an expression that I get for the Si dot Sj. Well, I mean, it's a long expression but very useful one actually. Now we use the semi-classical approximation taking S to be large. Okay, so we are already working in this limit of large S, so large spin we talk about. In this limit, the operator Ai becomes Ai is equal to under root of S into Bi plus Ai minus under root of S Bi. What we have done here is we have added under root of S into Bi and subtracted under root of S into Bi, where Bi is a constant which is determined by minimizing the Hamiltonian. Okay, the Hamiltonian that written down earlier. So substituting the expression for Ai that we have written down in terms of Bi into the Hamiltonian, and expanding in 1 by S. Okay, so remember that it's very important. S large, we are expanding in 1 by S. So to leading orders, the Hamiltonian is written like this. So you see here H is equal to minus summation over Jij into this expression which is there inside this square brackets, which contains all the constant Bi and Bj. Now the next thing that we need to do is to find the ground state. Okay, this is usually we do that for any Hamiltonian, that the first thing that we do is to find the ground state. For that we will make some approximations so that we can tackle this complex Hamiltonian easily. Assume that all Jij are positive, this constant. Further assume only nearest neighbor interactions and all these constants Jij are same j. So we replace all these jij as simply j. So everything, I mean, irrespective of which site it is, what are the nearest neighbors, everything is the same. Also, all the bi are same. So that is basically we are assuming, like really a homogeneous and system where everything is same. So what we do is that the ground state then can now be found like this. The expression that is shown here, E naught. E naught is equal to minus j L z s square multiplied by, in square brackets, mod of b square into 2 minus mod of b square plus 1 minus mod of b square whole square. And I can see from here that all these indices are gone, I and j. So irrespective of where we are, everything is the same, which is equal to minus j L z s square. Here z is the coordination number of each lattice side and L is the total number of lattice sides. Okay. So the ground state is independent of B because the spins can rotate in any direction so long as they are all point together. Okay, very important. It's independent of B. Why? Because the spins can rotate in any direction so long as they are point together. Now what we do is that once we have calculated the ground state, we now include the next higher order in the Hamiltonian by treating the operator A as small. Okay, so we go one order higher. So in the previous case we were able to calculate the ground state, but now we go a higher order. So the Hamiltonian H is approximately equal to minus Ljz s square minus this term which contains these operators minus 2j summation over this triangular bracket actually indicates that they are the nearest neighbors. If you remove this, then it means that you are taking into account all neighbors, first next nearest neighbors and so on. But when you have this, then basically that implies that it's a next nearest neighbors only multiplied by, so this is summation over s, in the brackets you have this term where you have all these ai and aj's. A factor of 2 appears because each pair appears twice. Okay, important, a factor of 2 appears because each pair appears twice, and in this Hamiltonian the first part, if you look at it, it's a ground state. So the first part of the Hamiltonian is a ground state which we have already calculated. Okay, now we go beyond, so ground state and the next, now we are doing it. Now remember that in the previous Hamiltonian which we had described, we had only retained terms which are quadratic in these a's, okay, not cubic and the fourth power. We are happy with the quadratic because that's the next higher order. Now the Hamiltonian can be diagonalized by the following operator which represents propagating excitations. So in any case, like if you are given a Hamiltonian, then you need to diagonalize it to find the eigenvalues. And the trick here is that it's a propagating excitation, and naturally the propagating excitation can be written like this: ai is equal to 1 by under root of L summation over k ak e raised to power minus iota k dot ri. So this is basically something like a normalized representation where you get to see this under root of L in the denominator, and the summation is over all the modes, the k vectors, that is the k that we see here. So this yields the following Hamiltonian. Okay, so once you, so basically like you substitute back into this Hamiltonian, earlier Hamiltonian which we had described containing all these ai and aj's, and you get H is equal to minus L j z s square plus summation over k h cross omega k n k, where n k is ak dagger ak, okay, and the frequency omega, h cross omega, is 2 sj summation over this small delta vector 1 minus cos of delta dot k, where delta is the difference in the coordinates between the 2 points ri minus rj. So the frequency that we have written down in the earlier slide is basically what is called as the spin wave dispersion relation. Fine, I mean, like we write down, you can plot also the frequency versus k. But what is important here is to note that what is the value and how does it behave, this dispersion, at low energies. The low energy is, like, see, you have to differentiate between low energy and high energy. So we are very much interested in this low energy behavior. So for low energy, magnons. The frequency can be rewritten approximately as h cross omega is equal to Sj summation over delta square k square. So, look at this expression. This is a quadratic dispersion for specifically only for this low energy. And also note that as mod of k goes to 0, omega k goes to 0. These are known as the famous Goldstone modes. Okay, Goldstone modes have peculiar behavior that as k goes to 0, omega k goes to 0. So, you see that you know what Goldstone modes are now, that it is basically the low energy excitations of this coming from the dispersion of the spin waves. Now, this figure also beautifully illustrates the concept of Goldstone modes. So, on the top figure you will see that you have all the spins pointing up, okay, and then on the right hand side as you go you tilt the spins, all three of them, by a same angle, okay. So, what is this happening? Zero wave number, okay. Earlier they were pointing up, now they are pointing in a different direction, but they are all in the same direction, either you talk about the left one or the right one. So, the energy cost is 0, there is no energy cost here in this case. Now, if you go to the bottom, again on the left hand side you have all the spins up, but when you take it to the right you will see that all the spins are not tilted in the same angle. So, for example, the first spin is still pointing up, the second spin is slightly tilted to the right, and the third spin is slightly more tilted towards the right, okay. So, you get a small wave number, that is the wave number of the sum total on the right hand side is not the same as here, okay, there is a difference. So, this costs energy, the small wave number, and that is exactly the Goldstone mode. So, students, what you have studied here in this module is the concept of spin waves. So, magnons are quantized magnetization density wave. Then we also have studied how to use the Holstein-Primakoff transformation to solve the spin Hamiltonian, in which spins are represented by bosonic operators. The spin Hamiltonian is solved in the large spin limit. The large spin is very important because when we were solving it, we were expanding in 1 by s, okay, to generate the spin wave dispersion relation, and from the spin wave dispersion relation we could then sort of go and find the Goldstone mode. So, thanks for visiting ePathshala. Thank you very much.